Hello, my name is Aubrey Johnson. I'm an exercise physiologist and a doctor in clinical physiology and metabolism. And today I'm going to talk about resting metabolic rate, its importance, its definition, and how to calculate it. So, before we talk specifically about resting metabolic rate, I want to let you guys know that there are about three ways to express it in research. So, first we have resting metabolic rate, we have basal metabolic rate, and then we have resting energy expenditure. And these are the three terms that I know of. So, resting metabolic rate makes up about 60 to 75% of what's called total energy expenditure. And backing up again, total energy expenditure is defined as the total energy expended in 24 hours. This is normally expressed in calories per day. So, resting metabolic rate makes up a lot of that total energy expenditure because what you should know is that when you're resting, your body is still functioning. So, your heart is still pumping blood to reach all your tissues, your kidneys are still functioning, your liver functions, and your brain still needs fuel to get stuff done. So again, approximately 60 to 75% of total energy expenditure. The next component of energy expenditure is the thermic effect of food. So you actually do burn calories breaking down the food that you eat. And this approximates about 10% of your total energy expenditure. And then the last component is what's called activity energy expenditure. And this is the most variable component. Activity energy expenditure doesn't just comprise the exercise you do, it comprises walking, it comprises doing chores, so on and so forth. So there are a couple other components of activity energy expenditure, but we're not going to talk about it in this video. So there are three ways to measure resting metabolic rate. And again, this is used interchangeably with basal metabolic rate and resting energy expenditure. So the first way to measure resting metabolic rate is using indirect calorimetry. So this is considered the gold standard for measuring resting metabolism. And in this method, we measure gas exchange at the mouth under a ventilated hood. So when we're talking about at the mouth, what actually happens is we have a participant under a ventilated hood and we have them connected through a tube to a gas analyzer to measure again gas exchange. And gas exchange just defines the amount of oxygen you're going to consume versus the carbon dioxide you're going to produce. This method is expensive, but it is very, very accurate. A lot of times in research settings, we use a device called the parvomedics, and I'll explain more about that in the next slide, or just a little bit more about that. So for the protocol, as you can see in this picture, a participant lies supine on an exam table while a ventilated plexiglass hood is placed over their head. So once it's placed over their head, we do have a little bit of plastic that kind of hangs over. So we kind of stuff it in, kind of like push it under the shoulders and make sure no air escapes. And then from there, the volume of oxygen, which is again consumed, and the volume of CO2, which is produced, is measured continuously. So the total test duration, and this is very difficult on a participant, is going to be between 30 to 45 minutes, depending on a university specific protocol. So in the first 10 to 15 minutes, these are used to make sure the participant reaches metabolic steady state. So even when you have somebody lying down resting, it takes a couple of minutes for your body to realize, oh, we're resting. Your heart rate's going to decrease. The CO2 you produce is going to decrease because you're relaxed. So once the 10 to 15 minutes is over with, the final 15 to 30 minutes is data collection. So again, VO2 and VCO2 are measured continuously. So, some notes about quality control. We have to ensure during this test, as the scientist, researcher, what have you, we have to ensure that the fractional expiration of CO2 remains between 0.75 and 0.85%. So, we have a device within the gas analyzer where we can measure the flow rate. So if the FeCO2 decreases down to below 0.75, we decrease the flow rate of oxygen. And the flow, again, just comprises oxygen coming into the plexiglass hood. So from here, we're going to increase the flow rate so you have more oxygen coming in. And then if your FeCO2 is too high, we increase the flow rate, decrease. And again, this is really, really confusing. But again, we increase the flow rate to make sure that we have enough oxygen coming in. And if that sounded confusing, place something in the comments and I will break this down again. So from there, once we get all of our data points, we use what's called the Weir equation to calculate energy expenditure. And this equation is just shown below. And once you put everything in, the average values of VO2 and VCO2, you're going to get energy expenditure expressed in liters per minute. And in another video, I'll explain how we go from liters per minute to calories per day. So some additional output that comes from an indirect calorimetry test is the respiratory quotient. And this indicates substrate utilization. So the more CO2 you produce, once that reaches the more CO2 produced, the more likely you're burning more carbs. And then when you decrease that CO2 production in relation to oxygen consumed, you're burning more fats. At rest, most of the time, you're burning fats. So this respiratory quotient is going to be below 1 most of the time in a resting energy expenditure test. So like I said, BMR, RMR, and resting energy expenditure are terms that are used interchangeably, but there are some slight differences between basal metabolic rate and resting metabolic rate in regards to how they are tested. So, a basal metabolic rate test is conducted 12 to 18 hours after fasting. And from there, it is encouraged that the participant does not participate in physical activity within at least 2 hours of when you to actually conduct the test. The person before the test starts is required to rest quietly for 30 minutes before we even start clicking buttons. And from there, we are required to collect at least 10 minutes of steady state oxygen consumption. So a resting metabolic rate is different just because the conditions are more relaxed. You can actually do a resting metabolic rate test 3 to 4 hours after a light meal and make sure that no strenuous activity takes place beforehand. Okay, from here, resting metabolic rate is going to be slightly higher than basal metabolic rate just due to those relaxed conditions. Another way to measure resting metabolic rate is using doubly labeled water. This method is very accurate for energy expenditure, but it is extremely expensive and it's not used for routine resting metabolic rate measurement. We're not going to talk about this much here, but if you guys are interested, please reach out to me and let me know in the comments. So, the most feasible way to measure or estimate resting metabolic rate is using predictive equations. And these are quite simply found online. You can put in your height, your weight, your age, and your sex, and you get an estimate of your resting metabolic rate. It's very practical and inexpensive, but the accuracy varies by verbatim population and individual characteristics. But at any rate, the revised Harris-Benedict equation and the Mifflin-St. Jeor equation are two of the very popular equations used to estimate resting metabolic rate. These equations were created by scientists that use a host of demographic data from various participants. Well, I'm switching this. They use a lot of participants and gathered a lot of their demographic characteristics, such as height, weight, age, and sex, and they developed these equations from there. And in the next slide, I'll explain what these equations look like and the importance of each term. So for the revised Harris-Benedict equation, we actually have two equations, one for men and one for women. And since we have the sex taken out of each equation, we can just focus on the terms weight, height, and age. I just want to explain the importance of some of these terms. So we see that the constant, or just the numbers with no terms by it, we see in men that it is 88, and for women, it is approximately 447. So from the jump, it kind of looks like women are going to have a higher resting metabolic rate, but you can see with the constants in front of the weight term, the height term, and the age term, that weight plays a significant role in our resting metabolic rate. Height also plays a role, but not as much compared to your age. So we can see by the subtraction here that takes place once we calculate, for example, 5.7 times age for men, that your resting metabolic rate is going to decrease with increasing age. And so I have these values here under each equation for men and women, just to encourage you to see if you can calculate your resting energy expenditure or resting metabolic rate on your own. And in another video, I will calculate by hand myself just to see if we get the same answer. So the Mifflin-St. Jeor equation is slightly more efficient because there's just one equation for everybody. So here we can also see that weight plays a significant role as this constant of 9.99 is higher than all of the rest. Height also plays a significant positive role. The taller you are, the higher your resting metabolic rate, which is kind of cool. But similar to the previous equation, your resting energy expenditure is going to decrease with increasing age. And finally, I'd like to note at the very end that 166 times sex automatically shares that the resting energy expenditure for men is most likely going to be higher than it is for women. As once you put 0 in for sex here, you eliminate that 166 calories. And once you place a 1 in there for men, you get 166 calories added to the equation. And so I also have values here that you can use. These are the same values from the Harris-Benedict equation for men. And I'd like you guys to place this in the equation to see what answer you get and compare it to the values you got for the Harris-Benedict equation. And again, this is another equation I'm going to calculate by hand in another video because I do love math. So some utility for the resting metabolic rate are it provides a foundation, or one, it provides a foundation for weight management strategies. Before you start changing your lifestyle, you need to know what your baseline is. This equation or this value also helps prevent underfeeding in clinical populations. So what this means is if you come to the hospital and you're going to be there for a while, a couple weeks, maybe a month or two, which is unfortunate. The staff need to know the bare minimum of how much you need so they do not underfeed you within that hospital setting. And it is also important to note that they don't want to overfeed you as well. So knowing your resting metabolic rate really does help in those situations. The resting metabolic rate is also useful for assessing energy balance. So as an example, athletes. You do need to know what you need bare minimum so you can go from there to increase your food consumption to account for the calories you're burning while exercising as well. And this equation or this value is very sensitive to metabolic adaptations. So this is going to change in response to how you change your diet, whether you're reducing the calories you consume or increasing the calories you consume. So this is a good test and retest equation that you can use and apply to your life. So four important factors influence resting metabolic rate. And again, I just want to note that there's so many interchangeable terms for resting metabolic rate. And these four are also like reflected in the predictive equations we just talked about. So as I shared, men are going to typically have higher resting metabolic rate. And this is due physiologically to greater fat-free mass. So as you saw in the Mifflin-St. Jeor equation, men automatically had higher estimates of resting metabolic rate. Body size is also a factor influencing resting metabolic rate, and larger individuals are going to expend more energy at rest. In addition, RMR is going to gradually decrease with age, and we saw that in both of the equations, both the Harris-Benedict and the Mifflin-St. Jeor. And then finally, while this wasn't talked about in the equations or at any point during this presentation, fat-free mass is the strongest predictor of resting metabolic rate, which simply takes out fat from the equation and includes metabolically active organs and skeletal tissue. Again, this also plays into the men having higher resting metabolic rate due to greater fat-free mass. So this was my presentation on resting metabolic rate. I hope you learned a lot, and I just want to let you know in the next video, I will talk about calculating these things by hand, just so you can see more of the relevance and the importance to knowing your resting metabolic rate. These are the references I used for this presentation, and I also want to note that all the pictures that I used came from Bing.com. Thanks for listening and learning with me.